Welcome to Advanced Strength of Materials. We'll be covering order Bernoulli beam theory again. And if you recall, beams that are slender in one direction, they're slender such that the length is pretty large compared to the cross-sectional dimensions. Those are considered beams that can bend. And we made the assumption that the cross section remains perpendicular to the cross section during deformation. That's one of the assumptions we made. We also assumed that the deflections can be represented in a way that they're an explicit function of the slope in a linear way. And what they end up showing to us is that the strain is also then linear to the curvature, and also then the stress becomes linear with respect to y. So that's kind of how we derive those equations of elasticity. And we also derive the moment equation, which is provided here. So moment equals EI W double prime. So moment equals EI W double prime. W is the deflection in the y direction in this case. And moment in this case is a minus the integral of y, the axial stress times dA. We then derive the elasticity equations, the equilibrium equations for a beam. And so what I'm going to do now, I'm going to switch topics and I'll cover asymmetric beams, how to deal with that. So I'm going to cover unsymmetric cross-section beams that have unsymmetric cross-sections. And so what that causes is you end up getting two moments of inertia that need to be considered, and there's more work involved. So before I cover unsymmetric cross-sections, let me show you an example of one. So in this case, you can see that I have an unsymmetric cross-section. So what does that mean? It means that this is not a mirror reflection about the y-axis or the z-axis, okay? And in this case, what we're trying to do, we're trying to determine for the dimensions provided here, we're trying to determine the centroid of this cross-section or the location of point C. We're also trying to determine the area of the moment of inertia of this cross-section. And then finally, the product of inertia. And so let me walk you through that process for this particular problem. That's going to be important for what I'll cover a little bit later. So let's start with the centroid of the composite area. And what I've done here, I have divided the cross-section into two pieces. One piece is this part number 2, and this piece over here is number 1. I've also created a coordinate system along the z-axis here, and x here with the origin right here where you see that. And I'll put the laser pointer here so you can see that's the origin of the y and the z-axis for portion number 1 and portion number 2. So what I will do then, I'm going to then calculate the location of the centroid using this formula. And this applies if you have more areas, then you will keep adding them, a sub I times zi, and then you'll divide it by the total area of the whole thing. The easiest thing for us to calculate here is A1 plus A2. That's a very simple calculation. So that's this area here, 0.015 times 0.415. And that area there is A2, which is 0.002025. And then you have this area for part 1, which is 0.15 times 0.015. That area is A1, and that's this number right here. The total area, A1 plus A2, is going to be this number plus that number, which is the number provided here, 0.004275. The area goes into the denominator. Now we will look at the numerator, which has A1, which I already calculated here, and then I have A2, which I have calculated here. And now I will then use Z1 and Z2, which is what we're going to be looking at now next. So, in fact, what I did here, I actually did the calculation for Y1 and Y2 in this particular example. So, you can do it for Z1 and Z2, but in this example, I'm doing Y1 and Y2. So you can see it here. That's what I did. So let's look at the location where Y1 is. So for part number 1, the centroid is right here in the center of this rectangle. So the distance from the bottom here to that point is 0.015 divided by 2 for part 1. And that's 0.0075. And then for part 2, we need to calculate the distance between this point all the way down here, which is really 0.015 times the half of this distance here, because we're looking at this rectangle. And that distance from here to here, just using geometry, I invite you to pause the video and try it. You will get the value of 0.0825. So very easy, you know this height is 0.015. You can determine this height as a total, so that's 0.15 minus 0.015. And that's actually a very simple calculation. And when you do that, you get 0.135 for this height here. Divided by 2, divide that by 2, you get 0.0675 from this point to this point. You then add 0.015 due to this height, and so that gives you the distance from the bottom to this point. That number is 0.0825. Now you're ready. Now you take A1 times Y1, which is 0.0075. I did the calculation there. Then you take A2 times Y2, and that gives you right here is the calculation. And then you add these two numbers done here in Excel, divided by the area, gives you 0.043, which is the height from the bottom here to point C. It turns out that when you do the calculation using Z1 and Z2, you get the coordinate to be exactly what it was from here to the top. You also get it from here to the right. So that point is actually exactly at 0.043, comma 0.043. That's the location of that point. That's the centroid of this particular cross section. The next step now, according to the problem statement, is to calculate the area moment of inertia. That is the very next step we're going to tackle now. And so what you can do is look at the moment of inertia of these two pieces separately. And now that I know what the centroid is, I can then use the parallel axis theorem to determine what the moment of inertia will be about point C.